Okay, so welcome back to another video. So today I created an integral for you guys. So we have the definite integral from 0 to 1 of x squared plus 3x plus 1 divided by x squared plus x plus 5 times e to the negative x dx. Kind of looks difficult from the exterior, does it? But it's actually not that bad than you think. So I'll tell you this. Long division, polynomial long division is not going to save you to the extent where you think it's easily computable from there. This is something we have to take into a little bit of a creative approach. And this is, well, something I figured out that this is actually quite interesting. I feel like it's worthy for you guys to see that you could actually utilize if you encounter, such class of integrands for this example. So basically, the gist of this is we're actually going to do something of a substitution, but keep in mind, I didn't say a variable substitution like a u-substitution. This is actually in a take that we're actually going to call this a function, and using that function as the substitution, we're actually going to do something a little bit different / creative to the point that it actually comes down so easy, and then once you come down to the computation of simply integrating this, hard integral that becomes easy to compute, then it's comes out to as a great value than you think. So with that, why don't we actually just jump right in? So we're not doing a u-substitution, but a function substitution per se. So let's say I call f of x, and we're actually going to let that be our denominator of our integrand. So x squared plus x, and then plus 5 times e to the negative x. Okay, so why don't we actually try taking the derivative of our function that we just put in? So f prime of x, so that means we have 2x, then plus 1, and then subtract 5. So of course, using by the chain rule, the exponential function over here. So minus 5 times e to the negative x. Where are we going with this? What was the whole point of taking the derivative of f prime of x if this function, this polynomial function, for example, doesn't actually yield us something that does not look similar to what we have for our, given integrand? Well, check this out. When I actually add these two functions together, our f of x and our f prime of x. So together, f of x plus f prime of x. So that means I have an x squared. Then I add x, so of course we're actually just adding the common terms, obviously. So x plus 2x, so plus 3x, and then plus 1, and then guess what? 5 to the e to the negative x, subtract 5 to the e to the negative x, 0. I add these two functions together, guess what? We just have something of the numerator over here. So in other words, in all this take together, if you put in the substitution like that, I have now the definite integral from 0 to 1 of f prime of x. Add this with f of x, and then all this being divided by what we just call f of x and then dx. Wow, doesn't this look easy, doesn't it? Let me stand over here. Now, doesn't this look a little simple, right? Because using some linearity and of course canceling some terms out, since we have an f of x and f of x over here, what we have now is just the integral from 0 to 1 of just f prime of x divided by f of x, and then simply plus 1, then dx. The 1 obviously is a very, straightforward antiderivative / definite integral to calculate, of course. So we have a f prime of x divided by f of x. Now, guess what? We can actually do something of a u-substitution that to the point that it'll make things a lot easier. So what do we call this substitution? Well, duh, we just let u equals f of x. And then of course, du is simply just going to equal f prime of x dx. And so we just put in the stuff together. And so I have now the integral from 0 to 1. So, well, I'll just leave that as an indefinite integral for now. And then we just plug in the stuff back together. So now putting everything back together, I just have 1 divided by u du, which of course that's simply just going to be ln of u. I'll put this in absolute brackets, and then putting it back together for our u equals f of x, so ln of f of x, which we said that this is just x squared plus x plus 5 to the times e to the negative x, and then compute your antiderivative 1, which is just x, and then compute your bounds from 0 to 1. So easy. There we go. We just have something that's now a lot easier to, solve and put in our values. So why don't we actually do that? So now put in 1, so I have ln of 1 squared plus 1 plus 5 to the e to the negative 1, and then close that off. Let me write the absolute value for this, and then plus 1. And now let's subtract this for the 0 term. So I have ln of 0 squared, and then plus 0, then plus 5 times e to the negative 0, which of course that's just 1, and then add this with 0. And as we see that I have a 0 here, so ln of 0 plus 0, and then plus ln of 5 over here, so subtract ln of 5, and then simplify everything out over here, so I have 1, and then plus 1 squared plus 1, which is 2, and then plus 5 to the, so ln of 2, and then plus 5 divided by e, and then subtract this with ln of 5. And if you want to, you can actually just simplify everything together just a single natural logarithm if you want to, but we're just gonna leave that the way it is. So therefore, that's actually our final answer for this strikingly, you know, from the exterior standpoint of an integral that looks difficult, but if you take things into, you know, another creative approach, you actually get something that's a lot easy to compute. And there we have it, our answer, simple as that. So yeah, that's pretty cool if you ask me.